much, Neil. This is the presentation on characterizing the wind resources at the Celtic Sea. I am Ribu Ghosh. I'm the data analyst for Celtic Sea Power. Um, just to take you through, this is pretty much the agenda. I'm going to run through a brief introduction where I'm going to introduce our organization, the projects that we have delivered so far. Um, just to give you a brief understanding of why we went for the project, what was the current level of understanding in terms of wind resource in this area, and then I'm going to introduce the data set.
Sorry, it's stuck on slide 1.
Wow, you're still stuck here.
No, you've jumped in the second slide now. You're good on the agenda.
Okay, can you see the agenda now?
Yeah, I can see the agenda.
Yeah, we can.
Yeah, that's the one.
Yeah, and then I'll just give you a brief introduction on the study methodology, and I'm going to share the results. We basically wanted to compare the data set with a model data on all these parameters, like a general comparison, the statistical distribution. We did a regression analysis. We did a brief description of the comparison of the directional parameters. And also the other events that happen, like shear and wear, which would have an impact on both the generation as well as the engineering design. And since this was mainly focused on de-risking early stage development risk, so everything will become evaluated based on energy production. And then we'll have a conclusion, and this will then lead to Wood's presentation on the wind resource model that they have performed with the data sets. So, okay, Celtic Sea Power, we are a strategic regional development organization. Our main focus is twofold. One is to accelerate the deployment of floating offshore wind in the region. And while doing so, we also wanted to maximize the economic benefit for the region. We plan to do this by addressing 4 major key challenges. One is zonal planning and consenting. Second is the infrastructure, port, and grid. We have a separate team that's working on that. Then sustainable regional industry and workforce development. This particular presentation and this bit of work is kind of related to the zonal planning and consenting. We are an autonomous subsidiary of the Cornwall Council. We have 2 offices, one based in Hale and one based in Pembrokeshire, and we have a total team of 17 people. We are the co-founder and board member of the Celtic Sea Cluster, and we are also the co-founder and member of the Celtic Sea Developer Alliance. We just delivered successfully 2 ERDF-funded projects, the one being the Cornwall Flow Accelerator, CFA, and the other one was the Pembrokeshire Demonstration Zone, a multi-connector offshore substation design. This presentation is mainly related to the first one, the CFA. Under the CFA, we carried out multiple environmental data campaigns, one of them being the wind resource campaign, for which we deployed 2 floating LiDAR systems in the water. And also we wanted to improve the fidelity of the whole project by having more data sets, and we managed to do that through data sharing agreement. So we have access to a third LiDAR data set from a developer. We won't be sharing much of the sensitive data of that in this presentation, but it all fed to the model which Wood's going to present after this. We also have carried out other data campaigns, like an ornithological campaign, which included a digital aerial survey and an airborne LiDAR, which helps us understand the spread mix and the flight height of marine birds. And it also captures some marine mammals. We've done some eDNA sampling for fish and marine mammals. Now, before we go on to the findings, we just wanted to know what we have at the moment. We have an ERA5, which is a free data set that's available, which is a global atmospheric reanalysis model. It is quite a continuous data, but it is quite coarse, and it only gives the wind speed and wind direction for 2 heights, which is 10 and 100. So these are the data sets that we get. It's not sufficient for what we are looking for. This is a GIF of mean wind speed in this whole area. You can see from 1979. And this is a GIF of an hourly. You can see we can have quite a rough data set, but the resolution is quite coarse and it's not sufficient because we don't have any information on turbulence for it, and it's available for two heights, which is 10 and 100. So not quite commensurate with the turbines of future, which we anticipate the size of them that's going into the Celtic Sea. We also have a ABP MER Met Ocean model where data are available. Data is available for free, which comes in the form of a shape file, which gives mean wind speeds and power density, monthly, seasonal, and annual for two heights, 80 and 100. This is a plot of the wind speed, which kind of shows all our these sites are pretty much between 9.4 and 10 meter per second mean wind speed. This is a power density. This is also coarse, and also this was a model which was run for a period of 1st June 2000 to 31st May 2007. So we don't have any concurrency with this data with what we have collected, but they do produce these kind of annual mean wind speed maps, and also seasonal ones. Another one we considered was NEWA dataset, New European Wind Atlas. This also gives you like time series data for multiple heights, wind speed, wind direction, and stuff, and also similar three-dimensional like microscale variables, wind speed, power density. This is where we plotted the mean wind speed for 150 meters, and I've also overlaid the Crown Estate PDAs, our LiDAR locations, and the test and demo sites. This is just a plot of the Weibull parameters, which they provide. This kind of leads to our floating LiDAR campaign, and we wanted to bridge the gap in the understanding and what we have. This is the LiDAR system being deployed on a very sunny day in Cornwall. This is where our LiDARs have gone. So this is LiDAR 1, LiDAR 2, LiDAR wins. We would call them WinC 6 and WinC 21. Going forward, these are the three PDAs. These are the test and demo sites. Our LiDAR buoys are also fitted with some additional sensors, like a wave sensor, a downward-looking ADCP, a wave sensor, a conductivity sensor, and a weather station. The LiDARs capture these data like wind speeds, wind speed dispersion, which is the standard deviation, min, max, direction, vertical components, and vertical component standard deviation. The acquisition frequency is all 1 hertz, like 1 per second. This is the resolution, accuracy, and range. And we wanted to compare that data set with the Vortex LES data, because Vortex LES data is is a data set that we procured from Vortex. It's a online meso micro couple data. It provides exactly the 10 minutes resolution that we are getting, and for all the heights, it can compute that we need to have a much better comparison with the data. This is where it kind of like in the wind industry, if this is a time characteristic length, then you can see what is actually of interest for wind industry. It's like the mesoscale and the microscale, and this is kind of falls right in the middle. This is like the schematic of the model, and this kind of gives all these points are where the validation has happened for this model for it to work perfectly. Before we introduce the study methodology, if there is any question, I can answer, or we can continue. Yeah. So as we described, we are going to compare these two data sets on all these parameters, especially our mean wind speed and the statistical P95 wind speed. We're going to segregate the wind speeds into 1 meter per second bins and see how them to compare. We're going to check if there is if the model data is capturing diurnal and seasonal variations. We will compare the statistical distributions and the Weibull parameters. We will do a regression analysis, and we are going to share some of the KPIs that we defined for the regression analysis, which we have taken from the Carbon Trust roadmap. And we will discuss a little bit about the shear profile, and and the shear profile alpha, and also we adopted a new method called the wind speed gradient, which is delta U by delta Z. We will define that and we will see how that works, and we will also talk a bit about veering. Mm. And because, as we discussed, we are going to finally evaluate everything based on its impact on generation. For generation calculation, we are going to use the IA 15 megawatt reference turbine, which was published by NREL, and then University of Mine has provided a similar turbine on a floating. You can see the hub height is 150 meters and a rotor diameter of 240 meters. This is the power curve of this turbine. Since it's an imaginary turbine, there's only one power curve. This is the cut-in speed of 3 meter, a rated speed of 10.59, rated power of 15 megawatt, and a cutout speed of 25. A standard way of measuring or like a rough estimate of generation is using the power curve and the hub height wind speed. However, the IC standards also mention there is a alternate way of measuring the generation. This is the rotor equivalent wind speed. This is ideally used where in sites which has high shear. This is how it is measured. This is the formula there, and there is documentation describing this method. Basically, what we do is, this is the rotor, the blue one, and these black dots are the wind measurement heights. So we see the LiDAR is measuring wind speed from 50 to 275, which are these black dots, and then we kind of segregate the whole rotor into horizontal strips, where each strip is kind of represented by the dot right in the middle. However, the length of the strips will vary. Once you go like in the middle ones, you see they'll have more weightage, which is captured by this formula. If you want to know more, there's this documentation available on this. Before we share the results, we also wanted to just give you into the on the data availability. So these are our two LiDARs, WinC6, WinC21. Unfortunately, WinC21, we had a power system failure, so we have lost a bit of data in the middle. We also had briefly a power system failure in January for WinC6, but they managed to get that repaired. But WinC21 was slightly difficult. We didn't have any weather window, so we had to wait for quite long and to miss a lot of data. This is monthly post-process data availability. These are the quality filters that we have used for calculating that. This is data availability within the 10 minutes bin greater than 85%, a signal to noise ratio greater than -23 decibel, vertical wind speed and vertical wind speed standard deviation less than 2 meters per second. Since we had a huge data loss in WinC21, this is the total post-process data availability. However, WinC6, this is the one much better. What is consistent in both that it measures the data availability is quite high till about 200 meters, and then it starts falling off the cliff. Now, this slide, we're going to just give you a basic comparison of some of the 5 parameters, like the mean wind speed and the P95 wind speed. We see the models consistently underpredict. However, the underprediction of mean wind speed is in around 2.5 meters, but 2.5%, whereas that for P95 is higher. This is a comparison for 100-meter wind speed mean and P95 between our measured data and ERA5. It is also underpredicting, but we see the underprediction percentage is much less. However, this does not mean this is a better model. This just means because this is the hourly data, so we had to kind of even out 10 minutes average data into an hourly, so that could have affected that. Now this is where we segregated the wind speeds into 1 meter per second bins. And for those same timestamps, we compared the model versus the measure, and this is the percentage difference. Now you will see that when it starts at lower wind speeds, the model is over predicting. However, because the value is very low, they are kind of exaggerated here. However, it kind of comes down to the slight over prediction at around 3, which is what we are considered, because this is the cut-in speed, and this is 25, which is the cut-out speed. So between 3 and 25, it kind of comes goes from slight over prediction to slight under prediction pretty much linearly, and then beyond 25 it starts kind of falling off the cliff. Similar observation, slightly different from WinC 21, and when we kind of plot only the significant heights, which is 100-meter, 150-meter, and 200-meter, it kind of behaves very similarly between 3 and 25, which is the region of the wind speed where generation happens. This is a time series plot which kind of demonstrates a similar behavior, where the red one is the model and the blue one is the measurement. You can see in these areas where the model is not only under predicting highs, and it's also over predicting lows. We just put 1 month of time series here, but similar observations is kind of seen throughout. This is the percentage difference now between 3 and 25. We haven't taken anything under 3, and we have taken anything over 25. For WinC 6, this is for WinC 21. We have fitted a linear regression model to it, and it shows very strong negative linearity, like pretty much all below minus 0.93. Now, this is then let's talk about the statistical distribution. This is the statistical distribution of WinC 6. These are the histograms. The orange line is our probability density function, and the green line is the cumulative density function. These are the Weibull parameters here, and these dotted lines measure, this is the P50, P90, and P95. We do the same for WinC 6, and this is all for concurrent timestamps. There's not much to choose here, apart from the slightly less with P95, P50, and the scale parameter. However, if we juxtapose one upon, we see the model is predicting a slightly narrower distribution with slightly higher peak. And the measured data is kind of predicting a slightly more wider and long tail distribution. Now, this observation is consistent across both the location and both the heights, which is depicted by this. So this is the shape parameter here. The model is consistently predicting higher shape parameter for all measurement heights, means the model is basically predicting a more right skewed distribution. And the scale parameter, the model is consistently predicting lower scale parameter for both locations and both heights, which means the model consistently predicts a more narrower distribution with higher peaks. Which will eventually also justify our first observation, where it is it is predicting lower mean wind speed and even lower P95 because of the distribution. We see the same trend across both location and across all measurement heights. Coming to the seasonal and diurnal distribution, this is the diurnal variation of WinC 6 in the dark blue line, and the same for the vortex LES data run for WinC 6 location. You see, it pretty much successfully captures the variation, and at no point the model is predicting higher than it is consistently under predicting throughout every hour of the day. We have similar observations for the other one. This is the seasonal variation, and it pretty much captures that as well. This is the same for the green ones or for WinC 21. Now, the issue with WinC 21 is, since we didn't have data for a very long time, so we don't have data between January and pretty much June, but from June to December, we have like double data. So this is meaned out of that. These are our observations, which we've already spoken about. So the model consistently underpredicts the mean and the P95 wind speed at both locations for all measurement heights, and more narrower and more right skewed distribution with higher peaks. and underpredicts high wind speeds and overpredicts lower wind speeds, and the model captures the diurnal and seasonal variations successfully. Next, we're going to talk a bit about regression analysis. So these are the KPIs which we have borrowed from the Carbon Trust of the accelerator report. So these are the two parameters. This is not a very conventional parameter, but this is the slope return from a single variant regression. By single variant regression, we mean when we force the regression line through the origin. And this is the coefficient of determination of the single variant regression. We also wanted to share the Pearson's coefficient, which is the correlation coefficient. These are the formulas that we use to kind of capture it. Now here we see this blue line. The solid line is for WinC6 and the dotted line is for WinC21. It's nothing much to choose, but it is consistently under 1, and it kind of like lowest at around 150, when it slightly rises, but it's still consistently under like between 0.96 and 0.97. So it's consistently under predicting, but the regression improves with height. This is the R square. The vortex LES data in this own validation reports kind of suggested they've got around 0.84. So our regression R square is like it goes all the way up to 0.88. So that is quite satisfactory. Now this is for all highs. These are the comparison. This is for WinC6 and vortex LES versus WinC6. This is vortex LES versus WinC21. These are the gradient for all the heights. These are the R square for all the heights, and these are the Pearson coefficient. Same with ERA 5. Again, we see ERA 5 gives a slightly higher R square here, but that is again down to the fact that it's kind of evened out into an hourly data from a 10 minutes. So that contributes to a better regression. Now, wind direction, we just wanted to include this couple of slides here. We defined these two KPIs. One is an absolute difference defined by this formula, and the other is the root mean square difference. Here again, we see for all heights, the absolute differences and the root mean square differences for both, it kind of decreases with height, suggesting better a prediction at higher heights. These are two wind roses for WinC6 and WinC21. This is the measured, this is the model, and this is a small GIF which kind of shows how, like, very minor, but you can spot the differences between them too. Observations, the gradient is consistently under 1 and the coefficient determination R square increases with height. Same with the Pearson R. Direction parameters, the absolute difference is between 14.4 and 16.5 degrees. The root mean square difference is between 26.3 and 30.9 degrees. Both decrease with height. The differences for WinC21 is slightly higher for WinC6, but which is contributed by the lack of data that we had between that 5 months period when it was down. I didn't see any questions here, so, and in the interest of time, I think I'll just continue. Now this is shear, and we are shearing is basically the change of wind speed with height, and veering is the change of direction with height. Traditionally, wind shear is kind of presented by these two formulas. One is the Prandtl logarithmic law, and the second is the alpha, which is the shear exponent. They both have like alpha is a dimensionless quantity, and these methods both have quite limitations, especially in offshore. This is just a plot of the vertical shear, and this is just the mean wind speeds for all this height. So it does show a monotonic increase with height. However, Like there are studies that suggest that that is not the case. There's a study that recently reported that in the North Sea, like anything other than monotonic shear is an abnormality of the that happens more than 65-70% of the time when you compute that over a 10 minutes average wind speed, and which is much higher than compared to what happens inland. So, and then there are other, the atmospheric boundary layer is much thinner offshore, so the modeling of like linearity cannot be applied. So there are a lot of challenges using this model to give you a complete understanding of shear. This is the shear they provide this alpha value of alpha that we got for WinC. This is the measure, this is the model. And again, same for WinC 21. It is still the model is under predicting minus 5.2% and 7.1%, but that is just the alpha. We will figure out what that means in terms of generation. We segregated the shear profile into 30-degree sectors. The model does capture this, but it still underpredicts slightly in the southerly direction, and especially southwest, which is the dominant wind direction. We need to find this out more. We borrowed this method, which is the wind speed gradient, which is delta U by delta Z, which is for every 10 minutes timestamp. We are identifying which is the highest wind speed, which is the lowest wind speed, and what is the height of the highest wind speed, what is the height of the lowest wind speed, and we are computing delta U by delta Z. This was an NREL paper which got published in 2021, and where it was actually studying low-level jets for US. We are not getting into that because that needs a lot more understanding of atmospheric stability, which currently I don't have the competence for, but it's still, there are elements that we could adopt from that paper. Now, once we have computed this delta U by delta Z for each timestamp, this is a plot of the distribution. Now, this is where we see the model and the measured data and the model have very different distributions. You see, the gray one is for the measurement, and in either cases, it's a much wider distribution with a much longer tail. You see this one, and this is because these are all 10 minutes average. So it could be a local storm, it could be some local disturbances. We don't really know what that happened, and I dare not use any that I don't understand. But the crux of the matter remains that the distributions are very different and quite similar for measured and modeled between the two observations. To understand what we would call a high shear event, we decided to have a threshold, again borrowed from the paper, which is the 90th percentile. And we see the 90th percentile for the measured and the model is quite, they are similar between these two, but you see it's 0.2021 and 0.015. It's again 0.02 and 0.014, and it has approximately 35% difference between them two. So anything above that is considered as high shear events. Like anything above 0.015 is a high shear event for the vortex data. Anything above 0.021 is considered high shear events for our measured data. This is the diurnal and seasonal variations. Now you see, because WinC6 is a more complete data set, WinC, but for months that we have data for both, they are consistent. We see the model is predicting higher shear events in summer, whereas the measured, whereas the model is predicting higher shear events in autumn and winter. March is very high. We don't have March data for WinC21, but for the third LiDAR, which had a complete data set, which we are not sharing at the moment, also confirms to this observation, March being the highest month with high shear events. Then again, this is here you see in summer, the model predicts higher events. And this is the diurnal variation. You see this the model in either case, the measurement in either case is kind of predict that it kind of increases with the day. It lowest in early hours of the day, let's say at 4 or 5 in the morning, and then it kind of starts increasing, whereas the model kind of predicts a more flatter distribution, goes up, goes down, but it does not like monotonically increase like what we have seen in the measured data. So we have spoken about this, and it kind of, yeah. And next, we wanted to see how these high shear events are related to turbulence. Now, for every step, we have also computed for this 10-minute step a turbulence intensity for 150 meter, which is a reference height. Basically, we divided the standard deviation by the mean wind speed. Now, this is in accordance with the paper that these high shear events happen at low turbulence, and you can see this dotted line is the P95 of the high shear events, a turbulence intensity, and the solid line is the P50 of the total a turbulence intensity distribution. Though the distribution of the turbulence intensity is very different, which is there are enough evidence to show that LiDARs and model, they don't calculate turbulence intensity in a similar way, and LiDARs might not be the best way to measure turbulence intensity. I still included this just to depict that this is both the model and the measure does suggest that these high shear events happen when there is less turbulence in the atmosphere. Same observations for the other LiDAR as well. Another thing that now we have very little understanding of atmospheric stability, and from what data that we do have air temperature sensor on the weather station, which kind of measures air temperature at 3-meter height from the sea level, and we have another sensor which measures sea water temperature. So this was one indicator that we have into atmospheric stability. So we kind of computed the air temperature minus sea surface temperature, TA minus SST. And this is the distribution of TA minus SST for the entire data. And this is that for just the high, and the green one is for the high shear events. Unfortunately, that sensor went down for our 2 data, so we don't have a whole seasonally balanced data, but it still does capture this one observation that this happens when the air temperature is higher than the sea surface temperature. That's when maximum high shear events happen. Same observation in WinC21, but again, we don't have a complete data set here. This is a scatter plot, and where this is DUD's delta U, delta Z along the y-axis. Along the x-axis, I am plotting this T air minus TC surface. This is the 0. It is not the best depiction of what we are talking about, but you can still see beyond when the air temperature is higher than the sea surface temperature, more these events happen. Just to give you a better understanding of how this looks, we wanted to include the same observation for the third LiDAR that we have, which has a more complete and seasonally balanced data set. You see now the distribution looks much more prettier, basically. And you see once your sea surface temperature is higher than the air temperature, this kind of tails off. Whereas when it is air temperature is higher than the sea surface temperature, most of these high shear events happen. Again, observation that both models predict high shear events occurring at low turbulence, and also happen where the air temperature is higher than the sea surface temperature. Second, and after that, we wanted to talk a bit about wind veering. Wind veering is the change of wind direction with height in the northern hemisphere. It is expected to move clockwise. The opposite of this, if it moves anti-clockwise, is called wind backing. We are expected to see wind veering, and this is what we have seen. Again, the dark blue line is WinC6, and the dotted blue line is the vortex LES for the WinC6, and same for the WinC21. The model predicts higher wind veering compared to the measurement. However, the model does capture the fact that there's slightly higher wind veering in WinC6 compared to WinC21. Here we are plotting the measurement height along the y-axis, and this is along the x-axis. We are plotting delta theta. Delta theta is the difference between wind direction from any height to the lowest height, which is basically from 50. So this is like, say, At the height of 75, the delta theta is around 2 degrees, whereas around 3.5 when we go to 100 meters, and that goes up to, say, almost 14 degrees here. Now, we then kind of segregated that into season, we divided it into 4 seasons. So December, January, February is winter, March, April, May is spring, and then 3 months summer and 3 months autumn. This is what we see here. So we see in lowest wind bearing in winter, which is captured by the model, but the difference is quite high. And only in spring that we see that the measured data is capturing higher wind bearing compared to the model. All the other 3 seasons, the model is predicting higher wind bear, and it's the closest between measured and model is happening in summer. So could be related to the actual wind speed, lower wind speed and less veering. This is the same for WinC21. Unfortunately, since we don't have any spring data, so we can't validate this observation where in spring it is showing highest wind veering. The measured data is showing higher wind veering than model. Apart from that, you see they kind of conform to what the observations are. Back to observations. The model is predicting higher wind veering across both locations. However, the model does pick up higher VIR for WinC6 compared to 21. WinC6, when segregated seasonally, again, we see higher wind veering in autumn, winter, and summer, and only spring measured data records higher wind veering. And it does pick up a seasonal trend of lowest wind veer in winter, then autumn, then summer, and highest in spring. Any questions so far?
Yeah, you got a question in from Will Rowley.
Yep. Yeah.
In terms of whether the data can be added to wave data to give an updated view on weather windows for installation risk assessment.
Oh yes, yeah, it can. So we haven't included wave data in this study, but and unfortunately wave data is the one data which was least affected by the data loss. So yeah, we can absolutely use what data we have can be used for weather window. We have done
Did you
this.
want to mention Did you want to mention the longer term weather analysis you've been doing as well, Rebe, in terms of windows?
Yeah, I haven't included that. So because we had an issue with sending a team to fix the LiDARs when they went back, and particularly for LiDARs, the weather window is even more difficult because it is kind of guided by safe working conditions on a tiny buoy. The weather windows will be slightly more for other bigger jobs. So what weather window we had was wind speed less than 10 knots and wave either less than significant wave height, either less than 1 meter and period greater than 10 seconds, or wave height less than 0.6 meter and wave period greater than 6 seconds. And we used so what we have seen from our wave data analysis is especially significant wave height is highly correlated with ERA5 data, where our R squares are in the excess of 0.95. However, the model is consistently over predicting your wave period. So ERA5 or any other model that we have seen is consistently slightly. There is always a slight positive bias when you compare it with the which we don't have an A. We can always calibrate the data, but based on ERA5 data from 1979 to 2022, we kind of tried to see the weather window availability, and it is consistently we have very little weather window in the autumn and winter months. So like that is one of the challenges of putting a LiDAR there. And if anything goes wrong, say in the month of October, you might not have a weather window to go and fix it maybe before April or May, however little, however insignificant the job is. So then that is another area that I wanted to cover, like especially weather windows are when the wind speed is low. Like so for say the LiDAR deployment, it was less than like 10 knots, but for slightly bigger jobs, it is when slightly higher, but it's still on the lower end of the spectrum. And you see that is one area where the model is consistently over predicting at lower wind speeds. So using like, though this presentation is primarily focused on checking whether the models perform well when it comes to energy generation, but we need wind data for other aspects as well, especially like weather window and engineering design. So that kind of puts slight question mark on how well these models are suited in prediction of weather windows, because if they're over predicting lower wind speeds, we might miss weather windows altogether if we are using models for that. So I hope I answered the question, but yeah, I will in our next where we could share more about the wave data and the weather window, and also we'll have the raw data available. So next roundtable we'll have more insight on that.
Okay. Did you want to add anything, Will? What's that? Oh, I can see you've responded in chat. Yeah, and certainly where we're seeing big effects and other considerations when we've been talking about these high production rates to meet our 4 or 5 gigawatt targets. That's a problem. When we think about getting turbines out from port to site, wet storage, that's definitely going to be a bigger issue than we thought.
Well, it is, but the only reason, and apologies for bringing it in, I didn't mean to cut across the whole point here, but what we're seeing in projects elsewhere is if we can't keep the operability to the right level, which is exactly your point, if it's something that's offline for 6 months, then it doesn't matter how better the rest of the months are, you're not going to make up for the operability. So it's a bit of a circular discussion to think about.
Yeah.
No, we have burnt our fingers in this, so we know exactly it's like we know the LiDAR can capture data. Just a minor needs to be done, but we just can't. Like there were people waiting, just couldn't go, and we'll have a glimpse of a tiny weather window. People would come waiting for it, and then it goes boom. Yeah. Okay, coming back to the yield comparison that which is where we want to see how the model actually performs with that. Now this table, in this first bit, we have used the hub height wind speed, which is the 150-meter wind speed with the IEA reference turbine power curve to measure the total generation for the concurrent timestamps that we had. And this is for the rotor equivalent wind speed. What is interesting is the model does underpredict slightly compared to the measured data, but if you see the underprediction is much less. Like where in terms of mean wind speed, we are seeing 2.5%. In terms of P95, we were seeing around 3.5% underprediction. Whereas when it comes to generation, it's 0.56% underprediction, and for WinC21 is 1.32%. Now, when we use rotor equivalent wind speed, it's again down to around 0.6% and 1.3%. So this does not really, like the shear does not really, though the model is slightly unable to capture the high shear events, which might have an impact on loading, it is not that relevant when it comes to generation. So in either way, and because all the massive discrepancies between measured and model happens at like wind speed ranges which are beyond where generation actually happens between 3 and 25. So the actual impact is much less, which is, and because it is consistently underpredicting. So any AAP calculation that is done using model is always going to be conservative. This is a plot which shows the monthly diurnal variation, where the solid line for WinC6, this is the solid line, say this is for January, a solid line is for WinC6, and the dotted line is for the model. There's nothing much to choose. There's no massive discrepancies here. I still kept this slide because I don't know, because I just liked it. And yep, these are the major observation. Also, if you see WinC21, the under prediction is slightly higher compared to WinC6. Just to check that, we removed the data that's unavailable for WinC21 also from WinC6, like that is between January and June. And when we computed that, the difference is again shot up to around 1.3, 1.4%, which gives us the confidence to say that this is probably higher because of the data loss. Also, I'm not sharing this, but also when we use that with the third data set, developer data set, it is much closer to this value than this value. So we can fairly conclude that in terms of generation, the model's under prediction is definitely less than a percent. So I'm in no position to say that whether it's good or bad, but this is just an observation, and this is like much lesser than the mean wind speed of the P95. Now with that, these are our two major conclusions that I have. One being that for the AEP or the energy generation, the model's performance is quite satisfactory, and it can be used either in isolation or in as a hybrid model where you have strategically positioned LiDARs and you kind of supplement that with model data. The whole idea is kind of for all the issues like the weather window we have discussed is to kind of move away from the standard practice of putting individual LiDARs at every development sites, which is not only time consuming, it'll cost you millions of pounds, and it comes with a lot of other challenges. Whereas this model data is much cheaper, like a few order of magnitude cheaper than there, and it is with every moment it is getting better and better. And so this is one area which could be used to not only reduce the cost but also reduce the consenting time, which is going to be vital if we want to achieve this whole goal of 4.5 gigawatt by 2035. We can't do things the way we are used to doing. And this, in our opinion, provides a very good alternative. However, having said that, the model still needs to be further investigated on its ability to be used in extreme analysis and for O&M planning and weather window prediction. This is one area where either we need to have ways to kind of use the model, or the model needs to improve going forward. But for energy generation, we do feel that this is one area where it does have a huge prospect. That is pretty much it from me. If I'm ready to answer any question. And yeah, if there's any question, or otherwise we'll take a quick break and maybe we'll connect back and pass it on to Jamie to present the wind resource assessment.
Yes, so do feel free to come forward with questions. We do realise there's quite a lot of information quite quickly in a number of slides there. But as we said, we're on hand. If you've got any questions, any queries, you want to follow up with us, please let us know. I'm very interested to talk to people about data access and further analysis. So please do get in touch.
Yeah. Like, well, the raw data is still not available with us, but we will get hold of it in hopefully this week. But the 10 minutes average like post-process data is available. It's available for download through the portal, and also like if we have a data sharing agreement with you, like we have it in place with quite a few people, and I can just share the data set with you with all the documents with it. Once the raw data becomes available, the same can also be passed on. So if you want to access the data, drop us an email and we'll figure out a way how we can. Yeah, we have a question here. The campaign started in June 2022 and it ended in 25th September 2023. the LiDARs have come back, and we don't have any data beyond any further data to be added here. But in the next bit of presentation, you will see how we have how Wood has performed this model, where whenever like new data sets like this is available, will feed into the model and improve the fidelity of the model. So we are hoping going forward, once the Crown Estate's 3 LiDARs are deployed in the 3 PDAs, we'll have access to that data. And any of the developers that we have signed a data sharing agreement and who has access to our data, if they do a LiDAR campaign, we will have access to that data. But these are, again, commercially sensitive data. So we can only share our data with you, because this is our data. This is it's an ERDF funded project, and we will share the data to anybody who. But with developers, if you have, it's just to make the sharing more even and fair. We will just get back to us. We will figure out a way.
And just you don't have to answer, obviously, but I'm sort of quite curious there if people have got views on jumping to the use of models and potentially ditching floating LiDAR for the yield analysis. Obviously, potentially that's a slight diversion to the way projects are being developed at the moment. Quite curious whether people think we're in that position, getting close to it. Do we need more data sets to sort of build and enforce the model before that becomes feasible? Not sure if any developers have got views on that. No? Okay. Yeah. Well, I said, if anyone does want to chat to us about that, it'd be great, because obviously we're not in a position to conclude how projects should be developed going forward. Yeah. We aren't project developers ourselves, so obviously very interested in any views around that area.
Yep.
Yep. Good morning, everyone. I'll just share my presentation. If you could just let me know that you can see that okay.
Yep.
Great. Okay, I'll get started then. So Rebu's kind of teed up everything that's gone before the wind resource model in terms of the wind measurement campaign. But Wood has also been working alongside Celtic Sea Power to produce a regional wind resource model that covers the Celtic Sea region that's of interest as part of this study. So I've been one of the analysts that's been working on this. My name's Jamie McCreth, and I'm a principal consultant at Wood, working in the wind industry primarily. So the presentation is basically going to give you an introduction to Wood initially, and also Wood's involvement in the project, what we've been doing up until this point. Then I'm going to give an overview of the measurement campaign that's feeding into our wind resource model. We'll then look at taking that measurement campaign and running a long-term correction on it to derive our long-term wind distributions. And then those wind distributions are what will feed into the wind resource model that we've developed. So then there'll be an overview of the selection of the wind resource model and calibration of it. And then ultimately what we're trying to do with this project is develop a wind resource model that's considered suitable to underpin a finance grade energy yield assessment. So we're looking at the uncertainty that's associated with that model, and then the suitability of that model to underpin a bank grade assessment. So Wood's involvement basically, so Wood's a global leader in consulting and energy and engineering services. We've got global capability working in all aspects of engineering essentially and energy markets. But from my side really, and for the involvement in the project, is mostly renewable energy specialists. So we've got specialists of over 200 people working in offices across the globe. Our team that's primarily focusing on onshore and offshore wind and also solar and hybrid developments are based in Glasgow, and we have a Reading office as well in the UK that works more on the latter items on that list, so the green hydrogen, waste energy, biomass and carbon capture. So we're well placed to work on energy projects basically from cradle to grave, from conception to decommissioning of projects, and also repowering if that's a requirement also. So Wood's involvement with the project, we started work in Q2 of 2021. And we've basically been involved in the project prior to the measurement campaign that Rebu's given us an overview of, during the campaign, and also after the campaign has been finished. And the presentation here is really going to talk about the analysis that feeds into this regional wind resource model, which was developed after the campaign ended. But you can see before we get onto that, we've run indicative energy yield assessments or wind resource assessments for the project. So that's using purely modelled data sets. We were involved in the wind measurement campaign design, and we looked at measurement strategy uncertainties in designing the campaign that would result in the lowest uncertainty based on the development requirements that we were advised on. We also helped with some of the LiDAR procurement and tender evaluation prior to the LiDARs being procured and deployed. And we also looked at developing a bankability roadmap. So that comes back to the bankability and suitability of this analysis to underpin an energy yield assessment that's suitable for financial appraisal. During the measurement campaign, we produced an interim wind resource assessment. So partway through the measurement campaign that had been going on, we took the data after around 6 months, run essentially the same analysis that we're looking at in the rest of this presentation, and derived a model. And then after the campaign had ended, we revisited the same analysis, rerun the long-term corrections, and then recalibrated the model. So that's basically Wood's involvement. And as I say, the rest of the presentation is really going to look at what we've done after the measurement campaign. So there's the wind resource assessment, which basically involves a number of steps. And I guess I wasn't quite sure what sort of level of technical knowledge people had that were going to be in the presentation, so I thought it was quite useful just to give an overview of generally the stages of analysis that we go through, from basically measurement of data to derivation of this model. So the first stage is there's the measurement campaign, where we take on-site measurements, whether that be from a remote sensing device, the LiDARs that we have in this case, or from traditional mast measurements. Mast measurements are more commonly put in place onshore, but there are a few locations where we have offshore met masts as well. The measurement campaign typically that's going to be used to underpin a bank grade assessment would look at a minimum of 1 year, ideally 2 years, to feed in, to allow for capture of seasonal variations in the wind conditions on the project. And as Rebu's already mentioned, when he gave a detailed overview of the LiDAR recovery, typically 85% is the minimum that we would find acceptable to feed into a bank grade assessment. So once you've obtained all of that measurement data, we need to process it. So there's all of the data analysis that Rebu's discussed, where we look at calibration of the data, correction of anomalous data effects, and then assessment of the wind speed, direction, shear, turbulence, directional veer, all of these characteristics that are going to define what the wind conditions and characteristics are going to be on site. So that stage is important from a turbine suitability point of view, but also feeding into the wind resource model that we're deriving here. And essentially, once you get through that data analysis step, you've produced what's really a cleaned or a screened short-term data set that you think is going to be representative of the measurement period at your project. You then go on and look at the long-term data sets that are available, and you compare those with your short-term, and we run a long-term correction. I'll go into that in more detail in the next slide. And then once you have your long-term data sets at your measurement locations, we then need to determine how the wind resource varies away from those locations. So that's where the wind flow model that we use comes into its own. So just a quick summary of the measurement campaign. I've left this one fairly brief, given that Rebu's given a detailed account of it. So Rebu mentioned WinSea 6 and WinSea 21 as part of Celtic Sea's deployments, but we also considered WinSea 23 as well as another one in our model calibration. So that's 3 floating LiDARs that are deployed in the zones that we have on the map. You can see there's multiple zones that we considered in our initial work. Zones 1A, 1B, and 5 were the primary targets. So that's the purple, the green, and the red towards the north of the map. They were the primary targets for us to focus on, given that they had the best wind resource and were basically designated as the most suitable for initial development. And with each of these LiDARs, we've got measurements from 50 meters up to 275 at roughly 25-meter intervals. So it gives you a range of measurements covering the heights that you would typically expect from lower tip height to upper tip height of any future potential wind turbines. And obviously, there's associated with those floating LiDAR buoys, we've got additional metocean and environmental measurements as well. The measurement campaign essentially covered just over a year of data. So from July for the 2 Celtic Sea deployments, and then from August for the other WinSea 6 that was deployed. And from our side, the analysis was focusing on deriving wind resource grids that are giving wind measurements over the project at 3 primary measurement heights that were of interest for future development. So that's 100 meters, 150, and 200 meters. And you can see in the table here, we've got the short-term mean wind speeds from each of these deployments, and also the data coverage. So I've given the data coverage at 150. You can see that it's actually right on the cusp of what we considered suitable, but I'll come back onto that later when we look at the model suitability. The only exception to that is WinSea C21. As Ribu had already mentioned, there was a power system failure on this LiDAR from January through to June, and we lost a lot of data. But we've, as part of the measurement campaign and data analysis, we've run inter-LiDAR synthesis and basically filled that gap. So we've managed to get the recovery back up to over 88%, which is considered appropriate for the project. And then there's just a summary below of the wind roses from these each of these LiDARs. Although they're separated by a reasonable distance, there's very limited variability in terms of the wind rose. So once we produced the short-term cleaned data sets that I provided a summary of, the next stage is to look at how representative they are of long-term expectation. So yeah, as I mentioned, measurement campaigns are typically short in duration. You ideally have, well, you would require a minimum of 1 year to provide a seasonal balanced data set. 2 years is much better or ideal. But obviously anything beyond that is great, but it's in terms of planning and costs that's involved in that, it's not always possible. So what we need to do is we take the measurements that are available from the site and we compare those to long-term data sets to see what the windiness was during the short-term period compared to long-term expectations, and determine how representative that short-term period is of what wind resource will be like over the long term. So you can see in the image over to the right, if we can see my cursor. So in this image, you can see the short-term period that we measured is shown in the red box here, and this is a sort of a zoomed in on a monthly basis. So you can see if we compare that to a 22-year long-term period that goes back to 2000, essentially one is saying this is what our mean long-term will be. Any points that fall above this yellow line are saying that year was windier than what we would expect long-term to be, and anything that falls below is less windy. So you can see that the measurement period is some of it was below, some of it was above. So you can see that it may be that the wind speeds during the measurement were slightly higher than we would expect over long term. Just to give an example, I've shown another grey box here. If we had a measurement period that ran from 2017 to 2019, the short-term period would actually be of lower wind speed than we would experience over long term. So in that case, the correction would be to correct the wind speeds up. In our case, the wind speeds are going to be corrected down because of the short-term period being windier than we would expect over long term. So in order to do that, to determine this, we need to look at the long-term reference data sets that we can correlate with the project wind speeds. And there are a number of options for this. We have reanalysis data sets, and the reanalysis are global measurements that are produced in a 3D grid, and it's basically hindcasting atmospheric conditions based on some ground-based stations. There's also mesoscale model data, so that's it's a numerical weather prediction model, and the reanalysis data sets, they generally feed into this as inputs, but then it's a little bit more advanced than the reanalysis data sets because it's a numerical prediction model. And then obviously there's ground-based reference stations that you can correlate with as well. The industry as a whole is generally moving away from these now. There's very limited servicing. Particularly, the UK is one of the best, but out with that, they're not generally well serviced, and obviously offshore, there generally isn't much available. So in selection of which data set you would choose, you need to look at the consistency of that data set. Ground-based stations in particular, there may be changes in instruments or changes in exposure, and then also of the quality of the correlation that you have between your site measurements and the long-term, and also the uncertainty associated with that, are all going to feed into selection of the most appropriate model. So for the project, we considered 3 main inputs. So we have the EMD WRF dataset, the ERA5 dataset that's already been mentioned, and also MERA2. So the EMD WRF gives us time series data over a long-term period, a resolution of about 3 kilometers grid over the whole of the globe. ERA5 provides the same, but it's at a 31 kilometer grid, and MERA2's roughly 55 by 70 kilometers lat and long. So the EMD WRF dataset, that's mesoscale, and the other two are reanalysis. So this one actually incorporates ERA5 into it. In the end, we went with the EMD WRF datasets, but we carried out validations using ERA5 and MERA2. So you can see in this image at the top, the 4 little kind of clusters around each of the LiDARs shows the 4 different nodes, but you can imagine these would cover the whole of this area at that spacing. So we chose the 4 closest nodes to each of the LiDAR deployments and used those to inform the long term. And then you can see here the correlations between, so this is a linear regression between the LiDAR dataset and the long-term reference dataset. The correlations are broadly comparable. So this is looking at WinSea 6. They're broadly comparable between each of them. MERA2 is generally lower quality of correlation than you see with ERA5, and then the ERA5 downscaled using the WRF dataset. In the end, we went with the best correlating EMD WRF datasets. I'll show that when we go through the next slides. So you need to select the data set, but you also need to select the long-term period that you find is going to be representative of your project. This graph on the bottom basically shows the slope trend. So if we have only 1, 2, 3, 4 years of data, you can see that there's quite a lot of variability in this graph, and that's because year in, year out, you're going to have variability in wind resource, and the longer the period of data set that you consider, the less variability in your mean you're going to have, because you've got a more stable long-term period. So it's basically just showing with increasing long-term periods from 1 year up to 22, we're seeing that the long-term trend is stabilizing. So really you can see that roughly from about 15 years, perhaps 13 years onwards, we're seeing a fairly stable long-term trend. In the end, we went with the period that covers 22 years, but we do test the sensitivity of the long-term prediction to different periods, and they weren't found to be sensitive. So once you've selected your data sets, you need to run basically a measure, correlate, predict. This is an MCP, which is essentially what you do is derive linear relationships between the short-term measured data set and concurrent data from your long-term reference data set. You can run this using different averaging periods. For the final analysis we did, we used an hourly averaging period. Some people use monthly, some people use weekly. It really doesn't matter. You basically select the period that gives you the best representation and the best quality of fit. So these just show some of the prevailing wind sectors from the project over here. And this is a correlation between reference data on one side and the site data on the other. And it shows you the R² values for each of those data sets. So that's one of the things that you consider when selecting your data set is the quality of these correlation fits. You also look at the magnitude of the adjustment that you're seeing between the short term and the long term. And also we need to look at what the wind distribution is going to look like. So this is the short-term measured distribution. This is wind speed, and then the frequency of occurrences. So it's a Weibull distribution. So you can see that it's not perfect Weibull. There's a few little bumps in it over the short term. So that's from the LiDAR measurement. This is the short term from the reference, so the EMD WRF data set. And you can see it still follows Weibull, but there's a little bit of variability. So these two are only from a year of data. And then if we look at the long-term distribution, you can see it's a lot more smoothed out, and that's what you would expect using 22 years of data compared to just 1 year where you might have anomalous data. And this shows the reason why long-term adjustment and consideration of long-term distributions is more appropriate for the project to give you a more accurate representation of what the mean conditions would be on the project. So this is basically the results of the analysis. The measurement periods defined at the top. So each of these, as I mentioned before, are just over a year of data, and with synthesis. The long-term reference source was EMD WRF mesoscale data set. And then the long-term period was 22 years, covering the most recent 22-year period. The quality of correlation varies between LiDAR. So you can see WinC21 has got a slightly lower quality of correlation, but that was improved with the synthesis. And these are the mean wind speed predictions. I've only shown them for 150 meters, but as we come on to the model calibration, you'll see the wind speeds that we've used going forward. So the thing to take home from this really is that you can see the short-term wind speeds are all higher than the long-term. So that demonstrates that the short-term period was more windy than we would expect over long-term. And the adjustments between each of these LiDARs is around a 3% downwards adjustment, 3 to 3.5%. And then just below shows the sort of typical long-term distributions that we think are going to be representative of the project. Again, you can see here, these are actually long-term wind roses, and there's very little difference between the short and long term, but you can see that there is slight differences between each of the LiDAR locations, and we'll come on to that when we look at the spatial distribution in wind speeds. So basically, at this stage, all we have is the long-term wind distributions at each of the LiDAR locations. So the next stage in the analysis is to look at the wind resource model. And what we're doing then is going to be trying to predict using the LiDAR measurements what wind speeds will be over a much larger area. So for this stage, you need to select a wind flow model. Reboot gave quite a fairly detailed account of how shear and veer all varies diurnally and seasonally, and that's a kind of characteristic that you experience in an offshore setting where the wind climate isn't really driven in the same way it is onshore by variations in topography. It's more driven by variations in the thermal gradient in the atmosphere. And because of that, offshore wind modelling typically uses mesoscale models. So it's a global climatic model that captures seasonal variations, diurnal variations, and height variations in terms of changes in atmospheric temperature, which is basically what's driving the variability. So for that reason, we looked at 3 mesoscale models. They're broadly independent, but they're all really considering the same global numerical weather model. So we looked at the EMD WRF models. The EMD is a company that provides these services. And Vortex is another company that provides another independent service. So the EMD WRF model is what we considered initially in the indicative assessment. As I mentioned at the start of the presentation, we did initial analysis before we had site measurements. This model basically uses ERA5 data and assimilates. We derived this using 20 years of ERA5 data. It gives a spatial resolution of 3 kilometers. So in the images, you can see each of the pixels in these images is 3 kilometers by 3 kilometers. And it can give us wind speed maps at heights of 100, 150 and 200 meters, which is what we're interested in the project. The only drawback with this model is that all it gives is over the whole area, it will only give you a mean wind speed. There's nothing else associated with that. So then we went on to consider the Vortex farm, which is using the same weather and research forecasting model, so that global climatic model. It's assimilating 10 years of ERA5 data, and it's got a much finer resolution, so it's at 300 meters rather than the 3 kilometers that we've got for the EMD WRF model. And this produces a wind resource grid. So rather than just giving a mean wind speed over the area, we're actually getting for each of those 300 by 300 pixels, there's embedded wind resource information. So you get a mean wind speed, you get on a directional basis, you have the Weibull characteristics. So that's the A and K. So A is the size and the shape, and K is the shape of the Weibull distribution. And you get that again at heights of 100, 150 and 200 meters. And then the END gas model is essentially the same as the Vortex farm. It's using WRF again. It's available at 250 meter spatial resolution, but given the large volume of data and the relatively low variability, this was resampled to 500 meters. And again, this also produces a wind speed map, and it has a wind resource grid associated with it at 100, 150 and 200 meters. So based on these 3 models, we didn't continue with the EMD WRF one. The main reason for that is, you can see in the map here, the high wind speed areas are to the north, and then there's lower wind speeds towards the south of the project area. And given such a large area, and we're seeing a small amount of veer just between these LiDARs, the veer that you're experiencing potentially around the Cornish coastline and then further south, there's a danger if you don't have the embedded wind rows and speed distributions that you're going to be incorrectly capturing the wind resource here. It also has a much coarser resolution, so for that reason we didn't proceed with that one. The next stage, so once we decided to continue with the EMD GASP and the Vortex farm data sets, we ran some cross prediction analysis. So this is basically testing the validity of the model and how well the model predicts wind speeds at the LiDAR locations. So what we do is, if we take WindSea6 as an example, we know that the short-term mean wind speed from the data set we fed in was 10.65. We're then using that to initiate the model, and we're using the modeled distribution to then predict what the wind speed's going to be at the other 2 LiDARs, so at WindSea 21 and at 23. So we're basically predicting how well the model is determining the wind speed at those other LiDAR locations. And that's basically what we've done for each of them. We've done for Vortex Farm and also for the EMD model. And you can see that generally the wind speed prediction error, so this is an absolute difference, is for the most part less than 0.5%, which is incredibly good. So it proves that both models are predicting at each of these LiDAR locations the wind speeds very well. So really there would be no issue proceeding with both of these models from an energy yield analysis point of view. The only drawback was that the analysis we've done here, the model is seeded using measurements from the LiDARs, but what we were producing is a calibrated model. So these models initially are uncalibrated. To allow us to calibrate it, you need to run a single calibration step or multiple calibrations, but then produce a single output, which is that wind resource grid. So the difficulty with that is the Vortex farm, because of the higher resolution, was only available in 2 separate analysis runs. So you can see in the blue square here and then in the red square. And because we only had measurements available in the northern part of the project area, there was no possibility to calibrate in the southern area. And for that reason, we ended up going with the EMD GASP model. But that's not a compromise in any way, I should say, is that both models showed excellent cross prediction in the areas that it was available. So they're both considered to be appropriate for proceeding with. So that's basically the selection of the model. So we've come down to the point of using the GASP model from EMD. The next stage is obviously to produce the calibrated model. So what we've done is we've taken the long-term mean wind speeds. So you can see these here for each of the LiDAR locations at heights of 100, 150 and 200 meters. Excuse me. And they've then been fed into the model. And essentially it's an inverse distance weighted approach that's applied to calibrate the wind resource model using these site measurements. So for each of these LiDAR locations, the model is calibrated to these wind speeds, and then out with the area that's bound by these LiDARs, the model is adjusted by a certain magnitude depending on the weighted contribution from each of these LiDARs. So with that, you're getting really good certainty on the model calibration close to the LiDARs, but obviously as you move away and the weighting changes, and obviously you can see there's a reducing wind speed, there's a gradient moving towards the south, the uncertainty does increase, and that's something that we then went on to look at, is basically an uncertainty assessment, looking at the spatial uncertainty that we would expect to see over the project. So the horizontal variation in wind resource has been validated using the 3 LiDARs, and by using the cross predictions, we basically predict less than 0.8% in wind speed between these predictions. So it shows that the model prediction is very good. I should say this is uncalibrated, not calibrated. So it's good. But the mean absolute error is lower still at 0.3%. As you saw in the previous slides, there's a higher wind speed in these northern areas and lower wind speeds in the southern areas, but generally over the full area, the variation in wind speed is actually fairly low, at less than 5%. So it's roughly about 0.6, 0.7 meters per second. So it's actually reasonably low, although it does look severe when you see the red to blue color ramps in the previous images. So effectively, the model is validated between each of these LiDAR locations, but as you move outside of them, there's less certainty, and the predictions may be biased. So what the map here essentially shows is, with increasing distance from the validated area between the LiDARs, the uncertainty increases, and we're seeing model uncertainties of roughly just over 2.8%. This basically shows that any development in this northern area, there's going to be good certainty in the measurements that are used, and it's going to be suitable to underpin a bank assessment. But as you move further south, there's going to be lower lower certainty, and it means you're going to have a higher uncertainty in your wind resource assessment and in your energy yield assessment. So the suitability of that to underpin a bank grade assessment is going to be slightly reduced. So effectively what we're going to summarize here is how suitable the model is to underpin a bank grade assessment. And I suppose something that I didn't really touch on in the start of the presentation was people always use the terms bank grade or bankable, but it's what that actually means. And it's basically describing high quality, low uncertainty analysis that's going to be suitable for underpinning a finance grade energy yield assessment for financing a project. So there's two aspects. We've got the measurement campaign and the long-term distribution that fed into the model, and then there's also the wind resource model itself and how valid they are in underpinning a bank grade assessment. So as I mentioned, we've got one seasonally balanced period of data. That is suitable for underpinning a bank grade assessment, but ideally 2 years would be advantageous. But we've seen from the correlations between the site measurements and the off-site reference data sets that we get very good quality of correlation. And we've run an interim analysis using just 6 months and also an analysis using the full year, 13 to 14 months. And there's not a huge difference in the long-term predictions. So it demonstrates that although we don't have 2 years, the 1 year is providing a suitable amount of data to underpin a long-term correction approach. The data coverage, as I mentioned, is less than 85% on WinC21, but with the data synthesis, this comes up below the threshold of 85%. So there's no issues really concerning the data coverage levels. Ideally, when you're running a yield assessment or wind resource assessment, you want to have measurements as close to or at hub height as possible, so there's less prediction error or uncertainty in the prediction of the hub height wind resource. And in this case, we've got measurements up to 275 meters, so that's covered off. So we have measurements near to hub height. The wind resource model itself provides a high resolution model, so 500 meters resolution, which is very high actually for an offshore project. As I mentioned, we've only got LiDAR deployments in the northern areas, so in the original zones 1A and zone 5, which was the primary initial area, highest wind resource for development. And in that area, we'd see really good model cross predictions, and there have been no issues in carrying out an energy yield assessment for a bank grade project in that using the wind resource model from in that area. However, as you move further south to areas that are over 200 kilometers from the LiDARs, there's a fairly high level of uncertainty that's introduced because we don't have measurements here. So it would be advantageous. I know Neil and Ribu have both mentioned that this is an ongoing and evolving model, so it's calibrated at the moment using the 3 LiDARs that we have available. But as more and more measurements become available in other regions through the Crown Estate deployments and others, this model will be refined to reduce the uncertainties we have in these lower areas and produce a robust model that covers the Celtic Sea development area. I don't think I've got anything else to say on this one, unless anyone's got questions that I can field. That's me.
Thanks, Jamie. That was great. Unsurprisingly, you explained that much better than I've ever managed to. So thank you very much for that one. We do have a question that's come in from Chris Hanford. So how are you calculating or quantifying the uncertainty as around 2.8% down in the south region?
Yeah, so it's largely driven by the variability in wind speed. So there's 2 factors. I'll maybe just skip back to the image, just bear with me. So you can see that the graph here shows just variability, and it appears that it's just variability in terms of distance from the area, but it does also factor in the wind speed gradient that we see across the area as well. The prediction over the area that's bound by those LiDARs is, we used a mean of 0.3%, and then out with that, I think it was 0.003 or 0.005. I don't have it in front of me at the moment, per additional kilometre that we're moving away from the area of certainty. I should say that this uncertainty also isn't just, well, it is just variation in the spatial distribution. It doesn't consider uncertainty associated with the measurement campaign or with the long-term adjustment. It's purely variation in spatial wind resource variability and the certainty we have in that over the area.
Yeah, absolutely. Yeah, and you said obviously the focus for us initially is that area where we're expected to see the development.
Yeah,
but we are working with Ireland and France for a couple of projects at the moment, actually. So we mentioned a lot about UK data sets, but there may be comparable data sets coming in from those other regions soon as well. So they're both motoring ahead now in terms of their own floating wind development. Okay, well, we haven't got any other questions for the minute, but as we mentioned earlier, do feel free to send them through to Reboot, actually, not to myself. And I'm sure JB will be able to respond to any questions later as well. There's really good presentations. As I said, 2 years ago, we were sitting here with no data, no real resource understanding. So I very much hope the project significantly moved that on, and we continue to improve it to go forward as well. Okay, well, we'll leave it there. As we said, slides and recordings will be available. But please get in touch anytime. Reboot, did you want to say something?
Yeah, and on just for like, yeah, so for anybody with we have a data sharing agreement in place if we want to access the final output of the work that would just like Jamie just presented, let us know and we can send it. So we have the georeference TIFFs and the WRG files for the 3 heights, that calibrated EMD GASP files. So I can, if anybody is interested, drop me an email and I can share that with you.
Lovely. Okay, well, thanks to everybody, and hopefully we'll all catch up with you again soon.
Yep. Thank you. Thank you.
Thanks.
thanks everyone. Bye.
Yeah. Bye.
Thanks, everyone.
Thank you.
Amy,
Cheers,
thanks,
mate.
Reboot.
Yes.